Lesson 31, Resonance and Sound. So first off, we're going to talk about standing waves. So actually, even before we start, I think what might be kind of a fun thing for you guys to do too is if you go grab those long springs that we were doing in lesson 29, you were going to be able to see what I mean by a standing wave if you grab that. So if you get just two people, so like you on one end and someone else on the other end, and when you're over here, if you just, how you made like a wave pulse last time, how you just went like that way and then back. You might have done this already anyway when you were playing around with the slinkies. If you go that way and then back, and then this person goes that way and back at the same time, what's going to happen is that you're going to have when you're moving this thing to the right, right, you're like, this is you over here, right? You've swung this slinky down that way, and then you swing it back, so you're making a certain amplitude go up and down like that, right? What's going to happen is that let's say when you move it up and then down again, or up, you're going to make a wave that starts traveling this way, like we've kind of talked about normally, right? Or I guess in this case, it's the bottom one. So A is going this way. What's going to happen is the other person over here is going to do the same, but they are going to make a wave that's coming this way. And what's happening here is that you've got these points where you're sending a wave this way, you're sending a wave that way, where they're adding up at these points and they're canceling at these points. Once you start like swinging it back and forth, it's gonna actually feel normal. Like it's gonna kind of get into a groove, and it's gonna kind of make a pattern that's gonna look maybe like this. Maybe not this many of these loops, but something like that, right? The reason why it just all of a sudden fits into that groove is that's called the resonant frequency. We're gonna talk about that in a bit, but it kind of wants to be there. So yeah, this is kind of what's happening. So a couple of terms here though that we talked about in the last lesson, but now looking at it in case of a standing wave, we are going to call nodes are going to be these points where they cancel. So one wave is canceling with the other, and you get these what they're called nodes. It's where like it looks like it's reflecting, right? So it's like canceling there. Antinodes are going to be these points where it looks like they're building on top of each other. So this constructive interference points. And number two is just kind of showing the same thing. It's kind of showing how if you had this wave of B going this way and a wave of A going that way, they are going to build on top of each other, and we're going to have constructive interference of these things at these points, destructive interference at these points. So nodes, antinodes. Okay, looking down a little bit here now, though. So like I was saying, when you start swinging that spring back and forth, it's going to want to fall into a natural or resonant frequency is kind of what it's called. And if you look down here, we've got something called the fundamental frequency. I'm just going to scroll down a little bit. The fundamental frequency is going to look like this, where you just have one big loop. It's fundamental because it's just like the first frequency. It just goes up and goes down at a certain frequency, right? Now, the next one here says overtone frequencies. So overtone frequencies are going to be these other ones. We're going to have these other harmonics, right? So if you kind of look at our picture here, we've got, well, 1, 2, 3 nodes. And it's going to look something like this, right? So the other thing you're going to see is these numbers going like 1, 2, 3, 4, 5. If you know anything about music, you might have heard something about like an octave, how you could pluck a string and it makes a certain note. So this is just like the string on your guitar, if you have a guitar. And this wavelength, like you can see that we've got, well, it'd be 1, 2, or like, sorry, that'd be 1 wavelength, and then you'd have 1 more wavelength. So there's like 2 wavelengths there. This would be a certain note on your guitar. If you had a different octave, so let's say you were playing like an E note, but like an octave higher, then what that's going to mean is that you're still going to have that many wavelengths, but it's going to be in a different overtone. So now it would just be this one instead. So that's number 2. So same, there's still two wavelengths, but the amplitude is going to be different on it. All right, so let's move on down here. Oh, and watch this video too, please. So click on that or watch it in the playlist. Okay, so the fundamental frequency is called the first harmonic. That's going to be just up and down with one loop, right? If we kind of look at the table we have here, so this would be the first harmonic, right? And it kind of looks like that, where it just goes up and down. We're going to call the first harmonic n equals 1. And you can think about n as being just the number of loops that there are there, right? So there's like one loop there. There's going to be 1, 2 loops in that one, 1, 2, 3 loops in that one. Okay, if you look onto the next column here, it says wavelength in terms of L. So if we call L the length of the loop that you're making, if I want to know what the wavelength of that is, well, the wavelength is going to be 2 times that. And you can kind of see that if I just kind of continued on making my pattern, so that the wavelength would come up. It would have kept on going down and then back up again. And that would be like one full wavelength, right? So if I wanted to figure out what the wavelength is, I need to go 2 times L. So I needed another L to get there. If that made sense. Okay. And if you ever want to like kind of picture a wavelength too, it always looks like an S, kind of like I have there, right? So in the next one, this is going to go like one wavelength would just be that, right? So that would be the length of it. That would be L. All right. Looking back over here though, frequency. Our minimum frequency is going to be, well, remember what frequency is. It's just like how many times does it go up and down in a second, right? So this is going to be the minimum one. This just goes up and then back down again. You can kind of picture that spring or that string or whatever going up and then down. So, and that's as small as it can ever get. If you go twice as fast as that, that's going to look like this one. So this is going, you can think about it this way, as it goes up and then down and then up again. So that has a frequency of 2 times the whatever frequency you had to start with, your minimum frequency. So hopefully that makes sense. And so let's look down at these ones now. So if we wanted to look at the third harmonic, so n equals 3, number of loops is 3. And now if we were thinking about this in terms of wavelengths, well, this would be one wavelength, right? So from there to there would be one wavelength. So if I'm picturing this in terms of L, L is the whole thing, right? L is from there to there. So the wavelength is going to be, well, 2/3 of the length. And it's going to be 3 times the minimum frequency because it goes up and then down and then up again. If we look at the fourth one wavelength would be half of this thing. So from there to there, that's one wavelength. So if I was thinking about this in terms of the length of it, it's going to be half the length. And then finally, on the fifth overtone, it's going to go up and then down and then out again. So this is going to be just 2/5 of the total length. But it's going to be 5 times the frequency because it goes up and then down and then up and then down and then up again. Okay, hopefully that made sense. So that's kind of just what we're saying here. So the first harmonic has half the wavelength on the string. So that's going to look like this, kind of like what we talked above. The second harmonic is going to be just equal to L. So in general, we can make this equation. And this equation is on your formula sheet. So take a minute to find that. And this one's going to be pretty easy if you get a question like this. So it says, what is the wavelength of the fourth harmonic on a 2.4 meter string? So all you got to do is, instead of n, replace that with 4. Right? So then you just put that in, you get 1.2 meters. So those shouldn't be too bad if you can kind of figure that one out. This one's going to be the same thing. It says a third harmonic standing wave appears on a 1.8 meter string, so a length, when the frequency is 32 hertz. And it says, what is the speed of a wave on a string? So remember, if we want to know what the speed is, speed's equal to wavelength times frequency. That's the only speed thing we have for waves, right? So as soon as you see speed, we only have one formula for that. So that it's going to be that. We know the frequency, we're good there. So what we're looking for is the wavelength. We need that before we can find velocity. So if we're going to find the wavelength, then we're going to just put it into our new formula. So it's going to be 2 times 1.8 divided by 3 because it's a third harmonic. So we get a wavelength of 1.2 meters. And then just plug that into V is equal to frequency times lambda, or wavelength. All right, resonance. Okay, so to picture resonance, I got a little gizmo here. So if you're looking at this thing, hopefully it's not kind of glitching out. I kind of noticed that some of them have been kind of glitching on the video part of it. So if you got, I got two masses on springs, right? And if you remember, if I wanted to know what the length, or sorry, the period for a spring system, that's 2 pi and then m over k, right? So period depends on the mass and the spring constant. So what I want to have is these the period of these things are kind of different, right? So we'd say they're out of phase. They're not really helping each other out much, right? So what's happening here is I got this is a driver. It's just bouncing up and down, and then we're going to see what's happening with these things. And gravity's turned off right now, so you don't really, it doesn't really affect it. Okay, so that's kind of what's happening. But now let's make these things have the same mass. So this mass is 5 kilograms. Let's make number 2 5 kilograms. All the way. Okay, so now they're the same. They have the same period, right? So if I end up with a frequency, right now this frequency isn't very good, right? It's not doing much for it. But if we end up getting just the right frequency started, so right now they're a little bit out of phase. I'm just trying to find the sweet spot here. Okay, so you can see that we've got points where they're in phase and then they're kind of getting out of phase. So I got to turn the frequency maybe up a bit. There. So now you can see that we have this constructive interference with both of them, right? They're both pushing up at the same time and you get that amplified effect. And then they kind of, the frequency of the driver is a little off from the natural frequency of these two things. So they kind of go off a little bit. But if I got this thing just right, it should be going to a max. I'm not sure if I need to go up or down. Yeah, that's pretty good. Right, so I'm getting like a max there, right? This is what we're talking about resonance. And if you've ever swung on a swing or something, what you're doing is you're matching the resonant frequency of you swinging back and forth. So if you were on a swing, right? So you're going to be swinging back and forth, right? When you kick your legs, what you're doing is you're matching the resonant frequency of the natural swing, right? That's why you go higher. So you're amplifying it. So that's what we mean by resonance. Another example is going to be here, where if you had a system set up like this, and you had a length A and a length C, and they're the exact same, and then you've got B and you got D that are the exact same. But so you start swinging A and C, since they have the same length, they're going to have the same natural frequency, right? They're going to oscillate back and forth with the same period. B and D are going to oscillate different, but they're attached up here. So what happens here kind of affects over here. So you're going to get these places where they're going to amplify each other when they're kind of lining up with the same period, or when their peaks are the same. But then you're going to get these points where they kind of start to cancel each other. Okay, so I've kind of got the spring version of this thing set up here now. So if I turn this thing on, so what I have here is like mass 1 and 3 are bigger and 2 and 4 are smaller. So it's kind of the same type of thing, right? Their period's going to be different because of the different masses. So if I push on with a certain frequency, you can see that 1 and 3 are amplifying each other, right? They're helping toward this thing. And then, you know, they get a little bit out of sync. They start kind of like not matching up, and they kind of start to destructively interfere. And then it goes through a pattern of starting to build again, where it's starting to constructively interfere. If I turn up my driver frequency, if I match the natural frequency of these things of like 1 and 3, it's going to start to go up. So I'm not quite matched right now because it's kind of messing with everything, right? But yeah, anyway, so this is resonance. So this can be really damaging though too. So this concept of you got something that, you know, is just bouncing up and down a little bit to begin with, but if you match it with just the right kind of like push that you can get up and down, you can get extreme forces happening on these things. So if I go up and start to match the frequency of 1 and 3, then you can see that like these are things are going like together, going way higher than like they normally would want to go, right? They're amplifying each other. And this process can be really damaging, like I was saying. So if you go down, actually, you can watch this now or at the end if you like. There's this thing called the Tacoma Narrows Bridge collapse. This was all due to resonance. This happened because the wind that was blowing on this bridge matched the natural frequency of the bridge and just became so out of control that it ended up making this whole bridge collapse. And all just because of this thing called resonance. Like this can be extremely damaging if you don't take it into account. Oh, up here. Okay, so watch this video too with the coupled pendulums. And now resonance and air columns. So what we're going to be dealing with is two situations. We're going to have something called an air column. It's just a tube that you've got. And one's going to be closed on the bottom, like these three. And then the next ones are going to be open on the bottom. So just a tube that has like an open end on it. The other thing that we're going to imagine is that we have a tuning fork. So all this does is give a certain wavelength of sound that ends up going down, right? And what we're going to picture here is that, all right, so let's say that, well, what happens anyway is we hit this tuning fork. And then if you have a certain length tube, what's going to happen is you're going to all of a sudden hear the sound of that tuning fork. If you hold it over top of your air column, it's going to get sharply louder. It's going to get all of a sudden, like, just if it's a certain loudness, it's all of a sudden going to get way louder than that. And the reason for that is because if you picture, let's say this longest one might be the easiest to kind of picture first, is that, let's say, so you hit the tuning fork, it's going to send a wave all the way down the tube. And if it's at just the right length, then it's going to hit right at the bottom of the tube. It's going to reflect off the tube this way and then go back up again. And what's going to happen is when it gets back up to the top, you can see that we had a max when it left and then we have a max when it came back. What happens is that now we have a max and a max. We get constructive interference. That makes this thing louder than it normally would have been. So that's why you hear this thing coming out loud. So there are going to be a few places where this happens though. So this is a situation where it would happen, where you can see it goes down with this many wavelengths and comes back up. But let's kind of start in order over here. So the first one that's going to happen is if it's a short little one where you hit it, it comes down the tube, it hits the bottom, it reflects, and it comes back up. So again, it's like a max and a max. Well, this first one happens at 1/4 of a wavelength. That's what that 1/4 means, like 1/4 of a wavelength. And you can kind of see that if I kept on drawing my picture here, this would be half a wavelength there. And then it would go up. Oh, I better scroll up a little bit more. And then be right, like, so we started, like one wavelength would start here, go down, and then come back, maybe up again, like over here. Like that would be one full wavelength, would be that, right? So this is only at 1/4 of the wavelength. So that's where the first one's going to happen. The next one is going to happen where you're going to get a maximum, is where it goes down, hits, and then comes back again like that. So this time we have, well, this would be half a wavelength to there. The next wavelength, like a full wavelength, would be right there, right? So what we're at here is 3/4 of a wavelength is where this is going to happen. And then the next one is going to be 5/4, and you can kind of look at that to see the same type of process happening. So you can see for these closed air resonance columns, it's going to happen at every quarter wavelength. So it goes 1/4 and then, sorry, I shouldn't say every quarter. It starts at a quarter and then goes up a half every time other than that. So starts at a quarter, goes 3/4, and then to 5/4. I'm going to give you guys a formula here in a minute if you're kind of confused about what's happening. Okay, so for an open air column, though, if you kind of look what happens, is that the first place this is going to happen is so the sound goes down from here and then stops. And it reflects kind of like off the other side there. I know it's kind of hard, but it's because we're looking at it in 2 dimensions. It should be like in 3 dimensions. But this would come back up again. And then that's when we get our first resonance there. So that's going to happen first at half of a wavelength. If you can kind of see that this is only half of one wavelength. So if I kept going with this, one wavelength would be, so keep going, like up to there again, right? Like that would be one wavelength there. So this is going to be just half so far. And then the next one is going to be at a full wavelength. So you can see this is one whole wavelength coming down and then to there again. So that's one wavelength. It's where the pattern repeats again, right? That's when you're talking about wavelength. So the pattern would start to repeat there again. Okay, and then the next one's going to happen at 3 halves. So we can make a formula out of this for closed air columns. We're going to say that the resonant length, so how long the tube needs to be when you're going to hear it become louder, with wavelength, and here's going to be our formula. 2n minus 1 times wavelength over 4, where n is going to be just 1, 2, 3, all the way up to infinity, right? So these are just our resonant wavelengths. So the first resonant frequency is going to happen, you would just put a 1 in there and then plug it into your formula. Open air column, you're just going to plug it into there. So notice that this one looks similar to the formula that we've done up at the top here, but it is different, right? Where was it? Up there. 2L over N was that one. So they look similar but different. On your formula sheet, I've actually written it up just like this. So make sure that you know these ones are for air columns. Okay, so here's the type of question you might get. It says the first resonant length, so a 1's got to go in. Yeah, so, a 1's got to go in place of N, right? Of a closed air column occurs when the length is 18 centimeters. What is the wavelength of sound if the frequency is 512 hertz? What is the speed of sound? So first off, we just got to choose the right formula for a closed air column and put a 1 in there. If you put a 1 into this part of it, that would just become 1 over 4. So our formula becomes L is equal to pi over, or not pi, wavelength over 4. Rearrange that for wavelength and you get 0.72 meters. And then as soon as it starts asking for speed, you know that you need frequency and wavelength. And if you do that, you get that. All right, this one says a organ pipe 3.6 meters long, open at both ends, produces a note at the fundamental frequency. Fundamental frequency is going to be n is equal to 1. What is the wavelength of the note produced? Okay, so again, you just got to put 1 in place of that, rearrange, and you get 7.2. And then it says if the speed of sound is that, what's the frequency? Well, we just need to use our formula, or the only formula we know for speed of waves. So if you're thinking about musical instruments and ever wondered why they sound different, if they're playing the same note but they sound different, the reason for that is because we've got something called like overtones, like we've talked about, and they're being superimposed on the fundamental note. So you can see that we've got the same kind of general shape between a tuning fork, a violin, a clarinet, and an organ pipe. And but there are these little dips and little things that are happening here too that are kind of making or changing things up a little bit. Um, you might ask yourself, like, why does this sound good? Well, that's kind of a deeper question, right? That becomes like, why did we evolve to hear things that have that kind of a wavelength sound good? Like, well, why does that sound good? When you think about it, that's all that music is just waves in the air. But for some reason, us humans think that is pleasant to hear, which is strange, right? Like, do dogs, do other animals hear sounds and get joy from it? Just waves that are happening through the air. It's kind of a strange thing if you think about it. All right, so go ahead and watch these videos. I'll make links; they'll be blue when I make these links here, and then go ahead and do the hand assignment. And that's going to be it for that lesson. So one more. We only got one more lesson, guys.